I know it has been a long time back, so you may have forgotten where we were and what we talked about. So, this is a Lagrangian versus, versus is actually a wrong word, versus Eulerian approaches. And I'll not go through the details again, but Lagrangian approach basically is a particle approach, and in this approach particles are followed and their properties are specified as a function of time. So we look at one particular particle, follow it, and then we, whatever property we say is associated with the property of the particle. For example, if we follow the position of the particle, and if we look at the derivative of that with respect to time, what do we get? Obviously, we get what is called as the velocity. And if we look at velocity of the particle, take its derivative with respect to time, we get the acceleration. So in a particle approach, once a particle is fixed, then we just observe the properties with respect to time. And what you realize is the laws which we have, most of them are written for a particle approach. The laws of physics which we have, that mass of a particle is conserved, which means dm by dt is equal to 0. Okay, so they are written for a particle. So that also we can write most laws of physics are written for particle or system of particles. What's the rate of change of momentum of a particle? Rate of change of momentum of a particle is equal to sum of external forces being applied on that particle. And we have a law for a system of particles, that external forces acting on a system of particles is equal to the rate of change of momentum of the system of particles. Similarly, we have a law for rate of change of angular momentum of a particle. That is related to the moments about that point, about the point for which you are taking the angular momentum. And the first law of thermodynamics, again, when we write dE by dt, that is for a particle. Now, the Eulerian approach is also called the field approach. And what you do is, if beta is any property, then you specify the property at all positions and at different times. Okay, so you have a domain of interest. There is the location is specified by x vector. So you specify the property at all x and all time. And the particle which happens to occupy that x at that time will have the property beta. That is how the two approaches are related. Okay, so the particle which is at x at time t has the property beta. And as we will show, if I look at the rate of change with respect to time from a particle viewpoint or from a field viewpoint, they will be different. Because, so, and the reason why the rate of change of properties will be different will be that the particle does not stay at the same x. It keeps on moving, and once it moves, then it will have the property, field property at that point, at that time. So therefore, the two will be different, and we will see how to relate these two. How to relate the two derivatives with respect to time will follow soon. Okay. So now, there are certain things which we, with respect to the field approach, there are certain terms and the first of these is, and particularly since we are talking in terms of fluid mechanics, we have this term called steady flow. And what steady flow means is, partial beta by partial t is equal to 0 for any beta. Now, what do we mean by a partial derivative? When I say partial beta by partial t is 0, what's the meaning of that? It's with respect, that means you're fixing yourself at a particular location. X is fixed. When I say partial derivative, this implies the space coordinate is fixed. So, you are at a particular space coordinate and you observe a property of the particle, or property, the field property, and that stays constant. And this happens at all points. Then we say the flow is steady. All points and all properties, because beta is any property. Now, this does not mean if I move from one point to the other point, beta can change. Because only restriction I am saying is partial by partial t is 0. I am not saying partial by partial x is 0. So, properties could change from point to point. But at any given point, properties will not change with time. If that happens, we say the flow is steady. Okay? So, and we will see, often we will simplify the flow by saying that the flow is steady. For example, if I open a tap, then when I start the flow, then it is unsteady, because initially there was no flow, suddenly water starts to flow. But if I keep the level the same and particularly not very high, then what you will find is there is a constant stream which comes and it does not change with time. So that becomes an example of a steady flow. But there we know, as the particle keeps on going down, its velocity keeps on increasing, because then it's under free fall. So velocity does change with time, but it is changing with space, not with time. It does not change with time, I'm sorry, for the whole field. It changes only with space. So that is what we call as steady flow. And similar to that, we have and the flow could be 1D, 2D or 3D flow. So in a 1D flow, beta in a one-dimensional flow, the properties will depend only on one spatial direction. So they could change with x, but they will not change with y and z. Okay, so that is what we call as a 1D flow. And similar to that, in a two-dimensional flow, of course, I've taken x and y as this. It could even depend. Maybe there's a case where it depends on x and z, but not on y. That will still be called a two-dimensional. So dimensionality also depends on the coordinate system chosen. So that is how we define 1D, 2D or 3D. So again, these are just some nomenclatures. See, for example, if I look at flow, if I look at a flow in a slowly diverging channel, and then suppose if the inlet velocity is u1, which is uniform, and then if it's a slowly varying channel, then what you'll, and if at the end, again the flow velocity is uniform equal to u2, then in such cases what you find is the velocity is changing with x. But it is an assumption that we assume that it does not change with y and z. And so this would be an example of one-dimensional, where properties are changing only with x. And then again, if things are not changing with time, it would also be an example of steady flow. And this illustrates that if the flow is steady, suppose if it does not depend on time, then it need not be the same at all points. It can change. And if I look at a particle, a fluid particle which comes in the inlet with a velocity u1, it is traveling down. Is the particle, so here when we look at the velocity is only a function of x. But is the particle acceleration zero or non-zero? Now, how do we think of the particle acceleration? We look at a particle and we follow the particle. if its velocity is changing with time, velocity of the particle. So now here if you follow a particle, is the velocity changing with time or not? A particle comes in here, has a velocity u1. As it moves down, its velocity becomes u of x, which is probably a specified function. And at the end, it becomes u2. So is the velocity of the particle changing with time or not? It is. So therefore, the acceleration of the particle is not zero. Even though this is steady flow, but acceleration of the particle is not zero. So that means there are certain more terms other than partial u by partial t, which will contribute to the acceleration. Is that clear? And we will show what they are. Again, not now, maybe after 2 or 3 lectures. Okay. So then sometimes we have polar cylindrical coordinates, which means we talk in terms of r, theta, z coordinates. So here, of course, what we have is we have seen these coordinates, the polar cylindrical coordinates, where things are specified at in terms of r, theta and z, not in terms of x, y, z. So here, if flow properties we will often come across situations where we have circular geometry. Now, because of the circular geometry, often things may not change with theta, and that happens because of symmetry. Of course, if I'm studying in a rectangular channel, if I use r, theta coordinates, then things will change with theta because the geometry is like that. But if it's a cylindrical, I'm talking of flow in a pipe, in a cylindrical pipe, in a circular cylindrical pipe. There, what we'll expect is things will not change with theta. So then, if that happens, we term the flow as axisymmetric. So in an axisymmetric flow, properties will be functions of only r and z. So in that terms, and if you are following cylindrical coordinates and you have axisymmetric flow, you could think of it as two-dimensional. But the same flow, if I look at it in x, y, z coordinates, it will be three-dimensional. Because things will depend on x, y, and z separately. So dimensionality may also be how you are looking at in which coordinates you are studying things. And we choose coordinates to make life simple. Okay. So after this, let's try to see graphical description of flow. Often, how the flow behaves can be inferred, a lot of information can be got if we have some sort of a graphical description or some sort of a visualization of flow. Do we have any examples or in real life where we can see some sort of a flow visualization? Have you come across any such thing? फ्लो विजुअलाइजेशन कहीं देखा, मतलब have you seen it anywhere? Have you seen smoke coming out of a chimney? So the smoke pattern tells you about the flow. If suppose flow is coming out only with a constant velocity or in some sort of a straight line, if you see a smoke pattern which is just coming up directly and is not jagged, so that tells you that the flow is probably laminar, it is not changing with the cross directions. But if you see a smoke pattern which is jagged or which is varying randomly, then that tells you that the velocity must be changing at different points in some sort of a random way. Similar to that, I don't know, if you have some flow, you put a potash crystal in a flow, what happens? You will see some lines being traced by the flow. Because potash is at that location, but whatever points cross that velocity, you'll see that there is a pattern. Now this pattern may be either straight line or again it may be curved, and that will tell you of what is happening in the flow. It gives you some sort of information. So there are some of these graphical descriptions of flow, and the first of these is called a path line. In a path line, is basically the path followed by a fluid particle. So you take one particle. Now, when I say take one particle means I'm talking of a specific particle. So what do you have to do? You have to label that particle. So here, when we say particle, it is specified by labeling it. And how do you label it? So you say particle at x0 at time t0. Okay? So once you say once I say x0 and t0, I'm talking of a specific particle. And then I follow its path. And this path is called a path line. Okay? Is that clear? That's a simple thing. We just follow the path of a particle, we get a path line. Now, suppose we are given the velocity field v x, y, z, t. And then we ask the question, how do we find the path? So given the velocity field, because again you'll realize in fluid mechanics, we will in general follow the Eulerian approach. So in fact, maybe I should write this also. Generally, Eulerian approach is used in fluid mechanics. And obviously the reason for that is you can't track infinite number of particles. Particles keep on. So now, how do we find the equation of a path line? We are given the velocity. Now, the equation of path line will be So if the velocity field V x, y, z, t is given, and this will also tell you how to relate Eulerian and Lagrangian for a particular variable. So equation of the path line is very clear. dxp by dt is equal to Vp. But now we have to relate Vp to V, because what is given to us is the velocity field V vector, not Vp as such. So now the velocity field V of x, y, z, t, this is equal to V1i plus V2j plus V3k, or we can use ui. We will interchangeably use 2 or 3 notations for components of velocity, or we could use Vxi for the components of the velocity field. We are going to use these 3 notations. If I am using the index notation, I will use 1, 2, and 3. Often u, v, and w are also used for the x, y, and z components. Or I may be more specific, I'll write it as Vxi, Vyj, Vzk. And all these are interchangeable, or maybe sometimes I'll use one, sometimes I use the other. So this is how the velocity field. Now, the vector xp, let me write it as now dxp by dt. This is the velocity of the particle which happens to be at x, y, z at time t. So this will be, the x component of the velocity will be equal to v1 x, y, z, t, wherever that particle is. Similarly, dyp by dt is equal to v2 x, y, z, t, and where x, y, z, and t represent the location of the particle. So now, so obviously x location, y location will be given by integrals. But how do you locate the particle? The particle was at time t0. At time t0, the particle was at x0, y0, z0. So at time t0, particle was at so actually what I should do is, since I have to take this, so I cannot write xp is just this, I have to write integral of dxp and integral of dyp and integral of dz. What I had written earlier would have been valid if there was only if it was not changing. But since the location particle changes, so therefore it has to be an integral. And now what are the limits? At time t is equal to t0, the particle is at x0. At time t is equal to t0, particle is at y0. And we want to find x at time, y at time, and z at time. So this will give me, if I know the velocity field and if I know which particle I am talking of, I can integrate like this and get x, y, and z as functions of time. And that will give me the path. Okay? Is that clear? Are there any questions on this? Yeah? Yeah, xp. So, but which one? Here? No, in the brackets? No. So, at that time, it is at xyz. So, that is why it is not xp, yp, zp. And that's how you are relating it to the field. So, you are given the field v1, xy, zt. So, this xp, that's why on the left hand side, I put that integral rather than just putting it at x0. Because as it changes, x, yes, and then you are integrating it over. Yeah. Pardon? Yeah. No, we are taking it the velocity field x, y, z, t as a function of time. So it is possible you can't even integrate it directly. It's possible that because if suppose velocity field is x, y, I plus y, j, k or whatever, so then you cannot even integrate it. And you may require numerical tools to integrate it. It will not always be possible to split it up. And the contrived examples which we expect you to solve in the exams will be the ones which you can easily split. Now, what will happen if the velocity, if it is a steady flow field? Then on the right hand side, there will be no time. Still, position will change with time, but on the right hand side, there will be no time. I'll complete the three descriptions and then I will give you some examples more. So, this is the first concept of path line. Now, if you have a long exposure camera and you take a picture, let's say there's some fluid spilled in the river or somewhere, and you put a light on one of the particles. And then if you take a long exposure camera photograph, that will give you a path line because that particle will be traced as a function of time. So here you are following particles. That is what a path line does. Now we have a second concept which is called a streak line. And in a streak line, what happens is particles I've written a lot. there are many particles which are passing a particular location. So in a time interval tau, which starts from 0, ends at capital T, particles have passed a particular location. And that location is x0, y0. Let's take a 2D example, and all questions will make 2D, not 3D, so that life is simpler. So particles which pass that location, and at time t, if we join all these particles, so the particle which crossed at 0 will probably be the farthest. The particle which passed at time 1 will be slightly later. Particle at time 2 will be somewhere else. And so if we then join all these particles, this curve is called a streak line. Okay? Now you'll say, why are we doing all this? Now, physically, a streak line is something which is very easy to get. I gave an example of KMnO4 crystal kept in a flow. If I put a KMnO4 crystal in a flow, the crystal stays at the same place. As water, let's say, passes KMnO4, it attains that color. At a later time, when I see a line which has come, this line represents all the points which passed the point where the KMnO4 crystal was. So that means the line which I get is a streak line. Another example, often we do flow visualization by hydrolyzing water. That means if I put a wire and I pass current through the wire, then it will break up and we will start seeing bubbles at that location. Now, if I see a line of bubbles at a later time, all these bubbles started from the same place. So the line formed by the bubbles will also represent a streak line. So a streak line, all these, I talked of the chimney flow. If I look at it from very far, the chimney head looks like a point. Let's say just a single, this thing of smoke is emerging from the chimney. Now the particles which have, this line which you see of the smoke pattern, all these pass from the same point. So therefore, the smoke pattern which you see is also a streak. Okay? How? No, so then there will be many streak lines. For each point from where the visualization is happening, there will be corresponding to that, there will be one streak line. So in fact, the example which I gave of current, so from each point, there will be a line, but then if you are able to follow the lines, if they mix up obviously, then you will not be able to get a straightforward streak line. So, so now here, once again, the basic equation dx by dt is equal to v1, dy by dt is equal to v2. Of course, if it's a 2D flow, then the third equation will not be there. It's still the same. But now, when you integrate this, what you have is so far, this is the same as the path line. this relation. But when you integrate, the difference is going to be in the boundary condition. In a streak line, when is the particle at x0 and y0? So the particle is at x0 at time tau, not at time t0. It is at a variable time. The time tau is going from 0 to capital T. So at time tau, the particle is at x0. And similarly, it is at y0 at time tau, it is at z0 at time tau. And you are going to find the x here and you are integrating it up to t. So y and t, z and t. And this is how you will be able to. So now capital T is constant. The upper limit is not variable, which was there in the path line. What is varying is the lower limit tau, which goes from 0 to capital T. So the variable here is the lower limit. And again, using this, once you solve one or two problems, it will become straightforward. So we'll look at these examples in the tutorial today. And the third description which we have is what is called a streamline, and which is a very commonly used concept. And streamline actually, streamline is a much maligned term in the sense that, at least in all your high school physics book, you look at flows and it says it's a streamlined flow. Have you heard this term? Well, it is a wrong term. Every flow has a streamline. But when we call it streamlined flow, what they are probably trying to say is that the flow, the streamlines are smooth, they are not changing. But streamline as a concept, what we have is that tangent to the streamline gives the direction of velocity if I have a flow and if I look at the, if there's something called a streamline, if I look at the tangent to the streamline, its tangent will give me the direction of velocity at that point. So this is very similar to magnetic lines of force. When you have magnetic lines of force, the tangent to the magnetic lines of force give you the direction of the magnetic field or whatever it is called. So for example, if the flow field is 2D, Vxi plus Byj, then tangent to the streamline means dy by dx of the streamline, and this will be equal to, it gives you the direction of the velocity. So tangent to the streamline will be equal to Vy upon Vx. So here for a two-dimensional case, it will be a straightforward thing that you will be able to get the streamline by this equation. So here now when we have this, so if we can separate, if Vy and Vx are such that x and y's can be separated, easily, then what you will get is when you, this can be written in the form some quantity dy is equal to some quantity dx, where on the left hand side you will keep only y's, on the right hand side there will be only x's. So if it is in a form like this is how this equation will take form. And here the limits will be, we will get streamline passing through a point x0, y0. So we have streamline passing through x0, y0. The lower limit on y and x will be when x is equal to x0, y is equal to y0. And you want to find the streamline, you will get an equation of x as a function of y. Now here, if t comes as a variable, if the flow depends on time, then time is treated as a constant because you get streamlines at different times. So the time will play a role. It is not actually a constant. At different times, you can integrate it, but during the integration, you will keep time, assume it to be a constant, and substitute various values of times to get streamlines at different times. So in streamlines, the initial condition, what you have to be told is streamline passing through one point. So that point has to be specified. So these are the three descriptions of motion. Now, let me give you a very simple example which will show you. Let's suppose that initially we have air which is blowing at some velocity units, let's say 5 I, and I should probably specify then the 5 meters per second from 0 to 5, and then it suddenly changes direction. So initially it was blowing like this, and then from 5 to 10 it becomes vertical. Just a contrived example. So here, if I try to find path line of a particle, now here the space doesn't matter because the velocity is constant. It is not changing with space, it's changing with time. So of a particle at, let's say, 0, 0. So how will the particle move from 0 to 5? It will move in the right direction. So it will move, and then from 5 to 10, how will it move? It will move vertical. So therefore, path line of this particle will be like this. The particle starting at time at 0, 0 at t is equal to 0. So first it moves like this, and then it moves up. This straightforward. Clear? Now, let's try to look at so this is from 0 to 5, it is horizontal, and from 5 to 10, it goes like this. streak line of particles which are passing through 0, 0. Of course, as I said in this example, the location doesn't matter. At times, a tau which pass this 0, 0 from 0 to 10. So now, physically to draw the streak line, I'm not using the equations here, but to draw the streak line, how do you do? First, you look at the particle which was at 0, 0, and then the particle which was at 0, 0 at time t is equal to 0. Where will this particle be at time t is equal to 10? So for first 5 seconds, it will move straight and then it will go up. So the first particle released or passing 0, 0 at t is equal to 0. The second particle which passed, let's say, at t is equal to 1. Okay? Where will this particle be for the first 5 seconds? For the first 5 seconds, it moves like this. And then so particle 2, which passes through this point, first it goes like this. For the first 5 seconds, and then it moves up. To 5, I've goofed up somewhere. So particle 2 which is there, t is equal to 9. एक second, I'm just... t is equal to 1 पे जो particle था, okay, हाँ. Now the particle which is released at t is equal to 1, what happens to it? For the first 4 seconds, it moves horizontal, and then what happens? Then it starts moving up. So the particle released at t is equal to 1. This is the particle which was released at t is equal to 1. For the first 4 seconds, it will move horizontal and then it will move vertical. Is that clear? Similarly, the particle released at t is equal to 2 will be here, t is equal to 3 will be here, 4, 5. And the particles which have been released or which pass from there after t is equal to 5, they will be moving just vertically. So, and this gives us the streak line. And you can clearly see the streak line is not the same as that of the path line. And what has caused this change? The change of velocity at time t is equal to 5. From 0 to 5, if I look at the path line, and if I look at the streak line of particles from 0 to 5, and suppose if no change had taken place, it would have only been straight line. They would have been the same. But because of the change, what we find is the streak line changes when velocity changes with time. Okay? Is this clear? Now, what about streamlines? Streamline, as I said, is a concept which does not depend on time, or in that sense that to find it's an instantaneous concept. So from 0 to 5, how will the streamlines look? The tangent is just velocity, so straight line, horizontal line. If you are looking from time between 5 to 10, how will the streamlines look? They will go vertically up. So streamlines, if you are looking at streamline passing through any point from 0 to 5, they will look like this, and from the streamlines will look like going vertically. And wherever that point, your location is, you pass the streamline passing through that will be a vertical line. Okay. Now this example also illustrates one more thing. If the velocity does not change with time, then what can we say about the three things? From 0 to 5, the velocity did not change. And the path line, streak line and streamline were all identical. And similarly, just from 5 to 10, the velocity did not change. So if you look at during that location, time period only, again, streamlines, streak lines and path lines were identical. But once the change comes and that change time is a part of your domain, then path lines and streak lines will not coincide, and they may not be, and also streamlines, because streamline will depend only on that time. Okay, so this is sort of, so in a steady flow, where velocity field is not a function of time, all the three coincide. So you can, and this is even for a general flow, not just a simple flow like what I've taken. And this you can, even if you try to conceptualize, if things are not a function of time, then path lines and streak lines and streamlines will coincide. And that is why the easiest to get is a streak line physically. But if the flow is steady, then streamlines are the same as streak lines and path lines. So even if you get a streak line for a steady flow, that will also be a path line, that will also be a streak line. So even though often we get streak lines, but the streak lines represent streamlines also. And streamlines are very important. Now another thing, two streamlines can never intersect. They can converge to a point, but they cannot cross each other. Why? Because if they cross, then at the crossing point, the velocity will have there will be two tangent directions. And you cannot have two velocities at a point. So two streamlines can never intersect each other. They can converge to a point, at that point then the velocity has to be 0. So it can be, but otherwise, but they will not never cross. You may apparently see streamlines crossing when in a 3-dimensional flow you try to see it on a plane. Then streamlines may look like they are crossing, but in a 3D flow, you'll have to talk of a stream plane. And because it has to be, again, streamline will have to be a representation of all the 3 dimensions. Okay. Now there's one more topic I want to do, which is needed for the tutorial. So some of the tutorial problems will we will look at the general expression for shear stress in a fluid. In fact, we will define shear stress in a slightly different way. But in some of the elementary problems which we solve, we have a law of viscosity which was given by Newton. And what he said was that shear stress in a fluid is proportional to the velocity gradient in the normal direction. So now this again is the law which Newton gave. And for example, let me specify it with an example. We know the law on the right hand side. I have shown a block which is kept on a surface. And here, if this block, a force P is applied, and here we know this is what we call as Coulomb's friction. Friction is equal to mu k n if the block is moving. Now, let us try to look at a similar thing, but there is a thin layer of fluid. You have a force P being applied. Between the block and the surface. Let us say the block is moving with a velocity v. Now, if we try to look at what is the shear stress at the, in fact, actually this friction which we write as mu k n, this is also the shear stress integrated over the surface. That is the force of friction. Now, here if we try to look at it, so this the velocity is in the x direction and the face is the y face. So, the shear stress is tau yx. Y is the direction, x is the direction of the force. So, the shear stress we are saying is tau yx. So, what Newton's law of viscosity says is this is proportional to dvx by dy. The velocity is in the x direction and you take the gradient in the direction parallel to the perpendicular to the surface. So it is tau yx, or the shear stress is proportional to dvx by dy. Okay, and if it's a thin layer, then this we will take it as a linear law. That means the velocity at if this gap is, let us say, delta, then dvx by dy will be taken as equal to v minus 0. Velocity at the top is v, velocity at the bottom is 0. V minus 0 divided by delta. So this dvx by dy will be v divided by delta. And the constant of proportionality this is what we call as mu, or the coefficient of viscosity. So this is called the Newton law of viscosity. We'll look at the general version of this. We are looking at very special cases. There's only one component of velocity, and we are looking at the gradient in the perpendicular direction. So this law, in some sense, we can generalize this as tau nt is equal to mu times dvt by dxn. So n is the direction perpendicular to the surface, t is the direction of velocity, and if gap is thin, a linear approximation is taken. Okay. So sometimes even in thin gaps, the linear approximation may not work, but at least as of now, we will take a linear approximation. And this may again be needed in some problems. So that's why I'm trying to do it now. See, you'll also look at examples like, for example, this case you will look at in the class. For example, there's fluid in between two cylinders. The inner cylinder is rotating with omega. The outer cylinder is fixed. And again, there's a thin gap between these two. So here, if you have to find the fluid has a viscosity mu, radius are given, and probably the height of the cylinder is also known. So here what you'll have to see is, you have to analyze the surface which is touching the fluid. Let's say look at the inner cylinder. So there are two types of surfaces, a vertical surface and a horizontal surface. They have to be identified separately. They have to be analyzed separately. Now on the vertical surface, which is the direction of velocity? V theta. In fact, even on the bottom surface, the velocity is only in the V theta direction. Omega r, which is, so it's V theta. And what is the normal to the surface for the vertical surface? R direction. So that means you are looking at tau r theta for this one. For this surface, it is tau r theta. When you do the same analysis for the bottom, what is the direction of the surface? Perpendicular to the surface. It is z. And which is the direction of velocity? Theta. So that means when you analyze the bottom surface, for this surface you are talking of tau z theta. Is that clear? So you have to do the analysis for the two surfaces, and again using the same relation. So on this top surface it will be tau r theta. This will be equal to mu times dv theta by dr. And for the bottom surface it will be mu dv theta by dz. And then you have to integrate this. Now what you will realize is the force will become zero. It is a moment which is being caused by the viscosity. Because you look at a circular element, on opposite ends the forces will be equal. So what the viscous forces are doing is they are causing a moment. So you have to integrate that moment to get the torque. So this will, examples like this will be done in the tutorial this week. Two types of problems, streamline, streakline, path lines, and some of these very simple type of problems. Okay? And the homeworks will be is based on this. So you can start looking at the workbook, the first chapter 1 of that. Thank you.